In this next problem, this is one of my favorite problems actually because it looks really daunting. So, first let's talk and make sure we understand the concept and what's being spoken about. First of all, W stands for wind chill. Now, if you don't know what wind chill is, go outside and feel what happens when the wind blows on you. Okay? It's a combination of the actual temperature outside and the wind blowing on you, and what does that feel like? And in certain situations, which is what we're most used to, um, is it makes it feel colder. If you go out and play in the snow up in Flagstaff and the wind starts blowing on you, it gets really cold, really flat, really fast. That's why it's called wind chill. Now, so what does T stand for? Well, that's the ambient temperature. That's the temperature of the air. So the temperature outside. So regardless of what it feels like to you, what does it feel like to a thermometer if you put a cup over it and don't let any wind blow on it, right? That's the temperature of the air. Okay. And then since we're already, on the topic, what does V stand for? Well, that is the velocity of the air. Okay. Now, I believe the temperature for this problem, if I remember correctly, is written in degrees Fahrenheit, and the velocity of the air is written in miles per hour. Okay, so it's all the English units. So therefore, the wind chill is, again, it's still in degrees Fahrenheit, but the difference is it's what does it feel like versus what is the actual temperature. Okay, so that's what this problem is talking about. Now, let's do it. Let's find W sub t. Well, what does that mean? Right? Use the words. Here are the words. This is the partial derivative of W with respect to t. So this is the partial derivative of W with respect to t. So what we need to do, W is our output variable, t is our input variable, which means any function that doesn't have a t is automatically zero, right? It automatically says this first term here, there's no variables, which there really is. It's t to the zero, but since it's t to the zero, the whole thing becomes zero, right? Plus the next term, this has a t, it's t to the first. So what does the derivative do? Take the one out to the front. So this is going to be 1 times 0.6215 t to the 0. But t to the 0 is 1, so that goes away. And 1 times that is just that. So really, truthfully, all we're looking at right now is 0.6215, right? Okay, next term, minus, minus, minus. Does this term have any t's in it? Nope, no it does not, so that is 0. All right, next, this term. Does this term have any t's in it? Yes, yes it does. It is t to the first. This exponent is only on the v. The v is a constant, so this is a super simple problem. It looks really hard, but it's super simple because all we're going to do is take the one out to the front, and so that's going to be 1 times all the other stuff. So that just leaves us with 0.4275 v to the 0.16. And we're done. So we can get rid of the 0 in the middle, right? So there we go. So it's just going to leave us with that. Oh my goodness, that is so simple. So now when I want to evaluate here, dw dt evaluated at negative 3015, what this is saying is everywhere you have a t, you're going to replace it with negative 30. Well, good news, I don't have any. Okay, so therefore, everywhere I have a v, I'm going to replace that with 15. So this is going to be what? 0.6215 plus 0.4275 times, that is the world's worst 5. Go away, 5. I don't like you. There we go. 7, 5 times 15 raised to the 0.16. So this is where we reach for a handy dandy calculator and we're going to get an answer. And I will pause the video while I do that. You don't need to watch me type stuff in. And that is the number I got, 1.280841969. All right, but let's not forget what we're actually talking about. That is the key to all this stuff, right? Interpretation. what is that 1.280814? All right, let's just say we're talking about temperature. So let's just kind of round it to, I don't know, two decimal places. So let's just say, what is that about? 1.3-ish? All right. So what does the 1.3 mean? Well, think about your units. Put this over a 1 and say my numerator is talking about dW, wind chill, change in wind chill. So if wind chill is what it feels like, the temperature feels like, and I have a positive 1.3, then going up in temperature makes it feel warmer or colder. Yeah, you got that. It's warmer. So therefore it feels 1.3 degrees Fahrenheit warmer per, now my denominator is 1 degree Fahrenheit. That's the temperature, right? So 1 degree Fahrenheit increase in air temperature, right? But can we stop there? No, I can't stop there, because was this formula dependent on any values? When I took my derivative, did I have to substitute in the temperature? Did it matter that it was negative 30 degrees outside? No, no, that didn't matter at all. What did matter was the velocity. So what was the wind blowing at? 15 miles per hour. So I have to, in here, I have to include when the wind is blowing at 15 miles per hour. So does that make sense? So if the wind is blowing at 15 miles per hour and it gets 1 degree warmer outside, so the temperature, the air temperature goes up by 1 degree, it's actually going to feel 1.3 degrees warmer. Cool. All right. So it feels warmer as the sun comes out, right? And it gets warmer faster than the actual air temperature. Great. Or you could look at it the other way. It was very miserable. As the sun was going down and the temperature went down by 1 degree, it actually felt 1.3 degrees colder. So you can interpret it either way, because they would both now be negatives, right? So a negative over negative makes a positive, but the interpretation would be if one is dropping, then the other one drops as well. So there we go. Now we're going to do this problem again. The exact same problem, exact same formula, except now we're going to do the derivative with respect to v instead of with respect to t. So I'm going to put I want you to grab the same formula, exact same formula, okay? And I want you to try the problem yourself. I want you to pause the video, see if you can do this derivative. It's a lot easier than it looks. Now, I cheated just for a second. I grabbed the equation and copied it right here, so that way I could have it visually easier for me. So it's harder on the screen. I can't look up too high. So I just did that. All right, now the derivative. We're looking for v's. This first term doesn't have a v, so that's 0. Next term, no v's. That's a 0. Next term, yes v's. Okay, so here we go. This is a negative 35.75 v to the 0.16. Sometimes this looks scary, and sometimes students say, I didn't know what to do. Well, it's just a power rule. The exponent's a 0.16, so bring it out to the front. So this would be 0.16 times a negative 35.75 v. Now, I have to do my exponent, which is 1 minus 0.16. Try again. That's 0.16 minus 1. There we go. That's a little different. And so what does that come out to? Well, 0.16 minus 1, that is negative 0.84. So this exponent just comes out to be negative 0.84. And that's it. Now, you can simplify these values if you want. Just pop them in your calculator and you can write them out as a single number. All right, so then similarly here, this is going to, again, be a 0.16 comes out to the front, right? Times 0.4275. Now, what do I do with the t? Well, the t is a constant, so I just ignore it. It's times t, just like I did with the 0.4275. It was a constant, it stays there. The t is a constant, it stays there. So then the v again is raised, so I have to do 1 minus, oh hey, good news, that's the same number, 0.84. And there's our equation. We have our derivative. So now, you know what? Negative 30 is really cold. I don't want to do negative 30. That seems really, really cold. And we live in Arizona. Um, let's do our other version of 109, right? Isn't that a little more realistic for Arizona? What if it was 109 degrees Fahrenheit out? What would happen if we changed the velocity of the wind, right? All right, so let's do this. Whoops, wrong notation. W sub V of 109, comma 15. So let's evaluate this. Actually, I will pop all these numbers into my calculator, but I will write it out this way. I'm going to fill in the numbers before I pause the video. So V stands for velocity, so we're still at 15 miles per hour at a negative 0.84 plus, here we go, 0.16 times 0.42775 times T. What was the temperature? 109. Oh, the days of summer. And the velocity again is still 15. Is negative 0.84. Okay, so you type that in your calculator and we're going to figure out what we're looking at. I'm going to pause the video while I do that. So what did we find here? What did we get? All right, so let's come back in. Let's do a little zoom in. So what does W sub V mean? Well, this is where I argue the Leibniz notation is so much easier to read. It's dW dV, right, over V. There we go. So we put this over 1, and now we put our units on it. This is the numerator's wind chill, so that's degrees Fahrenheit. The V is velocity, so this is miles per hour. So what is this saying? What is this saying? Well, this says that our temperature went up 0.18 degrees Fahrenheit. It got that much warmer. It felt that much warmer. Let me put the word felt. It felt 0.18 degrees Fahrenheit warmer when the velocity of the wind increased 1 mile per hour. Well, but we're not done yet. Did we have to plug in any values? Yeah, I had to substitute in for my temperature and for my velocity. So we have to include that. So we're going to say when the temperature is 109 degrees Fahrenheit and the wind is blowing 15 miles per hour. Okay, so does that make sense? As the wind blows harder, it gets warmer. Well, think about a convection oven. Okay, so the idea here is as the wind is blowing, it actually feels warmer when it's 109 degrees out. But I challenge you, go back and try this again, do the exact same problem again. But instead of doing 109 degrees Fahrenheit, take that out and replace that with 80 degrees Fahrenheit and see how that changes your answer. Do it again with, instead of 80 degrees Fahrenheit, do it with 30 degrees Fahrenheit, below freezing. That's pretty cold. See what happens to your answer. And what you're going to find out is there is some breaking point. It's somewhere in the 90s where the wind at some point doesn't do anything. The wind feels like a zero. It feels completely, it doesn't matter. It feels the same. But anything higher than that number, it actually feels hotter. And anything colder than that number, you're going to get a negative answer, which means it actually feels colder. It's when you are outside. Oh my goodness, let me tell you, when I was in Chicago and it was -1 degree out and the wind was blowing at 30 miles per hour, we screamed every time that wind blew. We're like, stop blowing. It went right through your body. It felt so much colder. So, but here in Arizona, when we experience it in the summer, the wind actually can make it feel hotter. Pretty fun, pretty interesting use, and that's why I like this problem so much. All right, I hope this helps. We'll see you in the next chapter.